So chapter 2 dealt with matter and how it was divided up into different categories, like whether it was a mixture or a pure substance. And pure substances were broken up into further categories, elements and compounds. So chapter 3 is going to delve a little bit deeper into more about the atom, like what makes up the atom and symbols for atoms and isotopes and ions and things like that. So in the early 1800s, John Dalton came up with some postulates about the atom. Now, nowadays, most of those are going to seem silly to a lot of you, but back in the early 1800s, they were pretty novel ideas. So, and they led to what's now called Dalton's atomic theory. So, according to this theory, atoms are tiny particles of matter. Atoms of the same element have similar properties, which are different from properties of other elements. So that's to say, if I have an element of copper in this hand and an element of sodium in this hand, they're going to have different properties to them. Elements of two or more different elements will combine to form compounds. So for example, water, H2O, it's going to be, compounds are composed of combinations of elements and atoms. And atoms are rearranged to form new combinations in a chemical reaction. So when a chemical reaction happens, the elements that are bonded together, the atoms bonded together in one compound, will rearrange and form new compounds. All matter is made up of atoms. The definition of an atom is an atom is the smallest part of an element that still has the properties of that element. So, for example, let's say I have a copper wire. So I'm holding a copper wire in my hand, and it's been totally cleaned. All the copper oxide layer is off the outside, so it's just 100% copper. If I took that copper wire, and let's say I have a magic knife that's very, very thin, and I started chopping up that copper wire, I'd get smaller and smaller and smaller and smaller, and at some point I'm going to get down to the smallest part of that copper wire, which would still have all the properties of that copper wire. Okay, and that's what we would call the atom. If we took my magic knife and we cut that atom up even smaller into the protons, neutrons, and electrons, then it's no longer going to behave like a copper atom, and it won't have the same properties. So an atom is the smallest you can make an element and still have all the properties of that element. So what is it that makes up an atom, and where do we find those in the atom? So atoms consist of a nucleus that's composed of the protons and neutrons. So if we look at this picture over here, well, let's just take a more global view of this picture. We've got lithium atoms. So let's say we've got a chunk of lithium metal, and focusing on how those lithium atoms are stacked upon each other. And if we focus just on one single lithium atom here, we're going to find out that inside that atom is a nucleus, and that's where we find the neutrons and protons. Outside the nucleus is where we find the electrons. So an atom consists of electrons in a large empty space around the nucleus. So that's one of the amazing things about an atom, at least that I think, which is they have a lot of empty space to them. So if this pink colored circle represents the size of the atom, there's actually a lot of empty space inside the atom. So atom consists of subatomic particles. The three that we're going to look at in this class are the proton, neutron, and electron. Okay, the protons have a positive 1 charge. The electrons have a negative charge. I want you to know the concept that's dubbed like charges repel and unlike charges attract. So if we look at this picture, these two protons here, and they show the arrow that they're trying to get away from each other. They repel each other. Two negative charges are going to repel each other because like charges repel. Unlike charges, however, attract each other. So a proton and electron are going to move and want to be near each other. Neutrons have a neutral charge, so there's no charge to the neutrons. Here is a table that I got from your book that tells you, kind of sums up what I've said. The proton has this symbol, a lowercase p or a p with a plus sign. Neutrons have the symbol lowercase n. Sometimes you'll see it with a 0 up here, meaning it has 0 charge. And electrons are this lowercase e with a negative charge. The relative charges, protons have a positive 1, neutrons are neutral, and electrons have a negative 1 charge. This is the actual mass of a proton, neutron, and electron. I'm never going to really ask you about that. If you remember scientific notation from, and if you're watching this video after you've had lab where we've gone over scientific notation, you can see this -24, which means you'd move the decimal to the left 24 places. Well, that is a very, very small number, which means protons, neutrons, and electrons have a very small mass in grams. There is another mass unit out there, which I'm going to teach you in a little bit, called the AMU. That unit is simpler to use if you're talking about really small masses like the proton, neutron, electron. So if we looked at that, you can see that a proton is approximately 1 AMU, a neutron is approximately 1 AMU, and an electron is smaller than that. So it gives you a better relative idea of how a proton and neutron weigh about the same, and an electron is quite a bit lighter than the protons and neutrons. The location in the atom, once again, protons and neutrons are found in the nucleus and the electrons are on the outside. What do I expect you to know from this? This is a lot of information. I want you to know that the 3 subatomic particles are the proton, neutron, electron. It's good to know their symbols. I'm only going to use these first 3. I mean, just the lowercase p for a proton, lowercase n for a neutron, and then this E with a negative sign for the electron. Until we get to the nuclear chemistry chapter. When we get there, a neutron is going to have a different symbol. I want you to know the charge on those 3 subatomic particles, and I want you to know their location in the atom. So the atomic mass unit, that's the AMU right up here. The atomic mass units are used to convert absolute masses to relative masses for easier comparison. So we'll talk about that a little bit more in a few slides. It turns out that 1 AMU is 1.661 times 10 to the negative 24 grams. So you can use this as a conversion factor to convert between grams and AMUs. I'm never going to have you do that in this class, so really you're not going to need this piece of information on this slide, but it gives you a good idea of the mass of an AMU compared to a gram. Nuclear symbols. Now remember the atomic symbols, the symbols for the atom are what you find on the periodic table. It's the either 1-letter or 2-letter. If I'm asking you for the nuclear symbol, I'm wanting a little bit more information. Mainly, what are we finding in the nucleus? So a nuclear symbol represents a particular atom of an element. It gives the mass number, which is the number of protons plus neutrons, so that you add up your protons and your neutrons, and that's the mass number. And they're going to put that mass number in the upper left-hand corner of the symbol. And then you put the atomic number, which is just the number of protons, in the lower left corner. So here's an example of that. This is sodium, and this particular sodium has a mass number of 23. So it has 23 protons plus neutrons, and it has just 11 protons. So some information we can get from a nuclear symbol. First of all, atoms are electrically neutral. So if I ever ask you for the nuclear symbol of an atom, that's going to imply that the number of protons equals the number of electrons. So atoms are neutral, so their protons equals the electrons. That won't be the case. In a few more slides, I'm going to teach you about ions. And ions do have a charge, so that means their protons won't equal their protons, and electrons won't be the same. But if you hear me say the word atom, that implies that they're the same and they're neutral. The number of protons in the nucleus is going to determine what the identity of the element. So, for example, on the previous slide, when I said the atomic number for sodium was 11, it has 11 protons, then if I tell you an element has 11 protons, you're going to know it's sodium, because it's the number of protons that identifies what element it is we're talking about. From a nuclear symbol, we can determine the number of protons, neutrons, and electrons for an atom. So here's a couple examples. If I gave you this nuclear symbol for oxygen, I'm telling you that it has 16 protons plus neutrons. And down here in the bottom lower left-hand corner is the atomic number, which stands for the number of protons. So we, right off the bat, the first thing you do is you look at this lower left-hand number. And you say, okay, that is an 8, which tells me there's 8 protons. So you would write that down. To figure out the neutrons, you need to take the mass number up here in the upper left and subtract the atomic number in the lower left-hand corner. So 16 minus 8 is 8, so that tells us there's 18 neutrons. So you'd write that down. And since this is an atom, it implies that the number of protons equals the number of electrons. So if there's 8 protons, there's 8 electrons. If we move over here to phosphorus, we know that there's 15 protons, so we can jot that down real quick. Since it's an atom, we can quickly write down 15 electrons. The neutrons here take a little bit more work. So to figure out the number of neutrons, you take the mass number, 31, minus the atomic number, 15. So 31 minus 15 is 16. So that tells us there's 16 neutrons. Over here for zinc, look at the lower left-hand number, 30. So there's 30 protons and 30 electrons. 65 minus 30 is 35, so there's 35 neutrons. So make sure you can make sure you're able to do that. Contact me if you're not, and we can go over it a little bit slower in an office hour or by email. Okay, ions. Ions are atoms or groups of atoms with a net electrical charge. So they no longer have the same number of protons and electrons. If we call the ions cations if the ion has a net positive charge. So an example, a couple examples here. Lithium, when it becomes an ion, becomes this positive 1 charge. And so we call that, it's the cation, lithium cation. Calcium here, when it becomes an ion, it ends up becoming a 2+ charge. So calcium ion has a 2+ charge. So a couple things. You're going to be doing your homework assignments online. It's going to be important when you type in your homework problems that you put the number before the charge when you're doing an ion. And what a chemist usually do is they tend to leave the number 1 off. So I on a test would never take off points if you put lithium +1 or 1+. Okay, that'll be fine for me. But in terms of using the software to enter your homework problems, never use the 1 when you're doing either a +1 or a -1. And then when you're doing the charge, always put, or if it has more than a 1, put the number before the charge. Okay, so cations have a positive charge, anions are ions with a negative charge. So here's a couple examples. Oxygens becomes a 2- charge. Chlorine would be a 1-, but notice I left the 1 off. So to determine the number of subatomic particles, protons, neutrons, and electrons, indicated by the following symbol. Now, I'm being kind of lazy here and I'm not giving you the complete nuclear symbol. Okay? If I ask you for the nuclear symbol, I want the mass number in the upper left-hand corner and the atomic number in the lower left-hand corner. But it turns out that you can get this atomic number from the periodic table, which I'm going to show you in a little bit. But if you look at your previous slide, zinc had an atomic number of 30. So everybody on your notes, go ahead and put 30 down here in the lower left-hand corner. That's always a good step to do, because it's really common for instructors to give you a nuclear symbol without the atomic number, because you are always going to have a periodic table with you during an exam, so you can just quickly get the atomic number from the periodic table. Okay, so atoms and ions of the same element have completely different properties because they have a different number of electrons. Okay, so this is a zinc atom. This is a zinc ion. We know that because this zinc has a charge in the upper right-hand corner. Okay, when you do not see a charge in the upper right-hand corner, that means we're talking about neutral zinc. Okay, and they both have totally different properties, so it's really important that if you're trying to convey to me zinc ion, that is different than a zinc atom. Isotopes. They are defined as atoms of the same element that have different mass numbers. So, same element, different numbers in the upper left-hand corner. Another way of saying that exact same thing is isotopes have the same number of protons, because they're the same atom, but they have a different number of neutrons. So here is a learning check. Naturally occurring carbon consists of 3 isotopes: carbon-12, carbon-13, and carbon-14. State the number of protons, neutrons, and electrons in each of the following. So I'm going to grab my pen. I kind of want to do a quick little side note too. There's 2 different ways for me to convey to you an isotope. I can either do carbon-12 like this, or I can actually write out the carbon-12 and put a dash with the 12 out here. So if you ever see the element name followed by a dash and a number, you need to know that this number that they're giving you is the mass number. And hopefully you have memorized the mass number is the number of protons plus the number of neutrons. Okay. So when we look at this, it wants the number of protons. Well, protons are easy. It's just this lower, the number in the lower left-hand corner. Do we see a charge up here? There's no charge in the upper right-hand corner, which means this is a neutral atom. Okay, so since it's an atom, that means the number of electrons equals the number of protons. To determine the neutrons, you need to subtract. So 12 minus 6 is 6, so that means there's 6 neutrons. If we look at the isotope carbon-13, once again it has 6 protons and 6 electrons. 13 minus 6 is 7. The isotope carbon-14 has 6 protons, 6 electrons, and in this case 14 minus 6 is 8. So notice, a couple things I want you to notice. These are 3 isotopes of carbon. We know they're isotopes because they're the same element, but they have different mass numbers. Or another way of saying that, same element, but different number of neutrons. All right, memorize that about isotopes. A lot of students confuse ions and isotopes. Ions are atoms that have a charge. Isotopes are the same type of atom, but different number of neutrons, or different mass number. So here's a picture showing you that. I'm going to get my pointer back. Here's a strip of magnesium metal. If we zoom in on that, we can see the atoms stacked on top of each other. It turns out that if you get a sample of magnesium, you mine it and you purify it, it turns out that magnesium in nature is found in 3 different isotopes. Magnesium-24, magnesium-25, and magnesium-26. Different elements in nature have different isotopes. Some only have a couple isotopes and some have a lot of different isotopes. So it just depends upon your sample of material. So here's a learning check. Which of the following pairs are isotopes of the same element? So I'm going to give you, I'm not going to give you a second. Go ahead and pause it, try to answer it, and come back and see if you did it right. So we're looking for isotopes of the same element. Well, for starters, we can rule off A right off the bat because they're not the same element. To be the same element, it has to have the same atomic number in the bottom left-hand corner. So B, they are the same element because they both have 6 protons. And they have a different mass number. So B would be the correct answer to this because they're the same element but different mass numbers. That's what makes them isotopes. We would throw out C because once again they're different elements. Question number 2, in which of the following pairs do both atoms have 8 neutrons? Well, to figure out the neutrons you have to do a subtraction. So 15 minus 8 is 7. And 15 minus 7 is 8. So these do not have the same number of neutrons. If I go down to B, 12 minus 6 is 6, 14 minus 6 is 8. They do not have the same number of neutrons. Let's look at C. 15 minus 7 is 8, 16 minus 7 is 8. So C is the correct answer to the second question. Okay, the atomic mass of an element. The atomic mass is written below the symbol on the periodic table. It gives the mass of an average atom of each element compared to carbon-12. So that's a deeper statement than what we're going to go into in this class. Okay, I'm not going to take us deep into how they determine the atomic mass and have you calculate it and things like that. But I would like you to know that it is based upon comparing the masses of elements to carbon-12, this particular isotope of carbon. And I want you to know that it's an average atomic mass, because remember that there's a lot of different isotopes for every element out there. So that's why you end up getting this decimal number, because you're doing this kind of averaging. It's called a weighted average of all the different isotopes out there. It is not the same as the mass number, so a lot of students will confuse the number below the symbol and think that it's a mass number, but hopefully that doesn't make sense to you because the mass number is the number of protons plus neutrons. So that's always going to be a whole number, just a counting number with no decimal points. The atomic mass, however, under the symbol is always going to have some decimal points. The atomic mass of chlorine is due to all the chlorine isotopes. So remember I said they figure out that average atomic mass by averaging all the isotopes out there. So it turns out that chlorine has 2 isotopes. chlorine 35 and chlorine 37. But they have a different abundance out there in nature. So they just don't take the quick little average of 35 plus 37 divided by 2 is 36. Notice we don't have 36 as the atomic mass. They take what they call a weighted average, where they take into account the different amount of abundance out there. So about 76% of the chlorine in nature is chlorine 35. And about 24% is chlorine 37. So they have a mathematical equation, they type it in there, and they get this weighted average of 35.45 is the average atomic mass of chlorine. Notice it's not a whole number. It is the average of the two isotopes. What do I want you to know from that slide? Let's go back to that for a second. Mainly, I want you to know that if I ask you for the atomic mass of chlorine, you're going to go to the periodic table and grab the number under the symbol. So I want you to have memorized that this is the atomic mass. Above the symbol is where you find the atomic number, which stands for the number of protons. So that's kind of the biggie right there from this slide. So I have here just a table from your book of some elements and their atomic masses. So most elements have 2 or more isotopes that contribute to their average atomic mass of that element. It turns out lithium has 2 isotopes, a lithium-6 and a lithium-7. If I were to ask you by looking at this average atomic mass, do you think lithium-6 or lithium-7 is more abundant? Which one do you think there is more of? Well, I'm hoping you can look at this atomic mass and say, well, that's really close to 7. So I bet there's a lot of lithium-7 out there and a small amount of lithium-6 that is bringing the weighted average down a little bit from 7 to 6.9. You're not going to have to do that on test. I just think that is kind of interesting. If we look at carbon, there's carbon 12, 13, and 14 out there, but the average atomic mass is almost 12. Which would indicate that most of the carbon isotope is 12, and there's just a little bit of the 13 and 14 that's bringing the weighted average up. So we know the protons and neutrons are located in the nucleus of the atom, and we know the electrons are somewhere outside the nucleus in a bunch of empty space. Are there any restrictions to where those electrons can be? So do you think that those electrons can just be floating around all willy-nilly around the nucleus, or do you think there's specific locations of where those electrons can be? And the answer would be that there are specific locations, and I'm going to teach you how to convey that. So according to Bohr's model, so Bohr's model was the first model of the atom that kind of depicted that the electrons had specific locations to be in. And what the Bohr atom did is it said that the electrons were located in orbits around the nucleus, similar to the planets rotating around the sun in an orbit. That was how the Bohr model did it. So, and they would say, this particular diagram I have for you is hydrogen, because hydrogen has 1 proton and 1 electron. And so they would say the electron would be in this first orbit. However, we've discovered over the years that the Bohr model is not accurate. We use it often because it gives us a good picture, but it's actually a little more complicated than that. Electrons want to have the lowest potential energy possible. Thus, they will occupy orbits closest to the nucleus, which we call the ground state. When electrons are as close to the nucleus as they can get, then we dub that the ground state of the electron. Unless energy is added to them. So let's look at this picture of hydrogen again. Here's my hydrogen proton in the nucleus, and here's my electron in my first orbit. Now that's as close as that electron can get to the nucleus. We would consider this the ground state because it's as close as it can get. If I gave this hydrogen some energy, I could actually get that electron to move away from the nucleus. Now it doesn't want to do that, right? Because opposite charges attract, and that electron is attracted to the proton in the nucleus. So I'm going to have to put in energy to convince that electron to move further away from the nucleus. So you can put in energy, move an electron up into a higher orbit, and we call that an excited electron, but you're not going to have to deal with that. Just know that the ground state is when the electrons are as close to the neutrons as you can get. So what happens if energy is added to an atom in its ground state? That's where we end up getting a lot of the colors that we see, is a result of the fact that when atoms you put in energy to get electrons to move to a higher energy level. When those electrons come back down to the ground state where they want to be, they give that energy off. Sometimes that energy falls into different wavelengths. So we have this whole electromagnetic spectrum of the different wavelengths of energy. And so the atom might give off energy in the ultraviolet light region or the X-ray region. Some of the atoms, however, will give off energy in the visible region, and that's when our eyes can pick up the different colors. So different energies of light have different colors. And for visible light, the red light has the lowest energy and the violet light has the highest energy. So, and that has to do with the gap between the orbit levels. It's a lot deeper than you guys are going to have to know. So what do I want you to know from that slide? Well, this next slide is going to kind of sum up mainly what I want you to know. Energy is added to move electrons further away from the nucleus into higher energy levels. And then energy is released or emitted when electrons move back down to the lower energy level. So if we look at this picture, here they're showing us barium. They're holding a chunk of barium in a flame, and barium is glowing this green color. Here's strontium. It's making the flame burn a red color. Okay, so you might wonder, where are those colors coming from? Well, it has to do with the gap, the energy difference between these orbital levels. And so the flame is giving the barium atoms energy and causing electrons to move out further from. This particular picture is showing that the electron had been moved from a 2 to a 4, and then when it relaxed back down to the second level, it gives off green light. Where if it goes from a smaller energy gap, you might get red light. Okay, so all you really need to know with these two last slides is that electrons try to get as close to the nucleus as they can, and when they're in that position, it's called the ground state, you have to put energy in to get electrons to move up to higher energy levels. When those electrons move back down to the ground state, they give off energy. Sometimes that energy is in the light region where our eyes can see it. So the Bohr's model has been improved. Energy levels are actually, we know it's more complicated than that. It's not just simple orbits. In fact, we don't even call those orbits anymore. We call them energy levels. Okay, so let me go back to one of these pictures. So this number 1 would be the first energy level. 2 would be the second energy level. Okay, so we don't call them orbits anymore. The energy levels are split into sublevels, and those sublevels are labeled S, P, D, and F. And this is a cool picture that kind of helps visualize that for us. So I want to spend a little bit of time on that. Here's campus, and you have a choice of a couple apartments to live at. I personally would prefer apartment 1 or dorm 1 because it is closest to the campus. I would have the shortest walk to campus. And it only has 1 floor to it. If I end up getting dorm number 2, which is going to take me a little bit more energy to get to, it has 2 floors or 2 sublevels. The third dorm has 3 sublevels, and the fourth dorm has 4 sublevels. So it's kind of like the dorm is the level. So if we went back to that picture, the first orbit would be dorm number 1, dorm 2, dorm 3, dorm 4. Those energy levels are broken up into sublevels, and the sublevels are given these letters S, P, D, and F. Now you need to know that S is the lowest energy floor. It takes more energy to get up to floor P and more energy to get up to floor D. So the maximum number of sublevels per energy level is equal to the energy level number. So if you are on energy level 4, then you're going to have 4 sublevels. Okay, so the unimproved Bohr's model of the atom. So this was what Bohr had first said. It turns out that the sublevels kind of complicate things a little bit. So here is the original kind of orbits. We call them energy levels that Bohr had come up with. He said there's 1 that's closest to the nucleus, and 2, 3, 4, and 5. The first energy level only has 1 sublevel to it, and that one's labeled S, just like our dorm. So if we went back to our dorm, the first floor only has an S to it. The second floor has the S and the P. So here's my second floor. It's broken up into an S level and a P sublevel. The third energy level is broken up into S, P, and D. Fourth energy level will have S, let's see, 4 is orange, S, P, D, and F. And then things get more complicated that we're not going to go into in this class. What I want you to see, however, is that there starts to become this overlap of the sublevels, where, for example, you might want to think that the 4D is lower in energy than the 4S, but it turns out the 4S is actually lower in energy than the 3D, meaning it's closer to the nucleus. Okay? In upper level chemistry classes, they have to use a trick to help themselves memorize this. We, however, are going to give you the energy of these sublevels on your information sheet that you're going to get with every exam. Okay? But you're going to need to memorize one thing. You have to memorize that there's a restriction on the maximum number of electrons that can fit in each sublevel. So if we're talking about sublevel S, so the first floor on the dorm, only 2 electrons can fit in that. So you must be a pretty rich person to rent out that first floor, because you're going to only have to share it with one person. If you're on the second floor, the P floor of the dorm, you're going to have to share that with 6 people, because the maximum number that can fit on the P level is 6. Maximum number of electrons on the D level is 10, and then the F can hold 14 electrons. Now this is the maximum that it can hold. It can have less than that, it just can't have more than that. Okay? So if you memorize this, we are going to be giving you the relative energy of the sublevel. So on your information sheet we give you this, which says electrons will first fill up the 1s sublevel, and then after that they move to the 2s, and then the 2p, and the 3s. So you just have to follow this from left to right to get the correct order. Okay? So ground state electron configurations. You're going to fill the electrons in the lowest energy level first. So that's what I was saying, left to right. And here's the procedure. So if I ask you to give me an electron configuration, this is what you're going to do. You're going to start with a bare nucleus. So pretend like you have no electrons. And you're going to fill the electrons into the lowest energy sublevel first. So we're going to put electrons into the 1s sublevel first. Then you're going to move on when each sublevel reaches its maximum number of electrons. So do you remember what the maximum number of electrons that could fit in an S is? And that would be 2. So after you put on 2 electrons into the 1s, you're going to move to the next category, which is the 2s, and you'll put 2 electrons on, because s's can only hold 2. Then you'll go to the 2p, and what is the maximum number of electrons that a 2p can hold? That would be 6. So it doesn't matter what energy level you're on. If you have a p, then the maximum it can hold is 6, whether it's a 2p or a 3p or a 4p. Okay, so back to the procedure. Fill your electrons into lowest energy sublevel first, then move on when each sublevel reaches its maximum number of electrons. Stop when you have run out of electrons. So really your first step is to go to the periodic table and determine how many electrons the element has. And then you're going to follow this from left to right until you have used up all your electrons. So we'll do an example here in just a little bit. But if we look at this, if we look at some of these I've got done here for you, let's focus on boron. If you look on the periodic table, the number above boron is its atomic number, which tells you the number of protons. Okay, so boron has 5 protons. If I ask you for the electron configuration of boron, you would say, okay, well, I'm dealing with an atom, because I'm only going to ask you electron configurations for atoms, so the number of protons will equal the number of electrons. So if boron has 5 protons, then it has 5 electrons. So you need to look at your information sheet and get right here the relative energies of the sublevels, and you're going to start from left to right. So you're going to put 5 electrons on boron. So you would first put 2 in the 1s, then you move to the 2s and you put 2, but then the s's can't hold any more than that, so you're going to then go to the 2p's. And the maximum number of electrons a p can hold is 6, but it can hold less than 6, and since we only had to put on a total of 5 electrons, we stopped with the 2p1. So I've left some room for you to do. I'm going to go ahead and write them in here real quick. You can pause the video and see how you do. So carbon, if you look at that information sheet, I'm just going to do a couple of them over here. It says the 1s is less than the 2s, which is less than the 3s, oops, which is less than the 3p, which is less than the 4s. So we're just going to work this from left to right until we've used up all of our electrons. You look on the periodic table and it tells you that carbon's got 6 protons, so it must have 6 electrons since it's an atom. I write down the 1s first, and now here's where you have to rely on your memory. You have memorized the s's can only hold 2 electrons. It's important that you make it a superscript up here. So we've used up the 1s's. What comes next is the 2s's. So you write down 2s, and from your memory, s's can only hold 2 electrons. So we've used up 4 electrons, so we only have 2 more left to go. And I did this wrong. In here should have been the 2 p's. Okay, so the 2 p's come next, and we know that they can hold 6, but we're only going to put two in there because we only have 6 electrons to put on. All right, nitrogen has 7 electrons, so it's going to look very similar to this, except instead of having 2 electrons in the p's, it's going to have 3. Oxygen is going to have 4 in the 2 p's. And fluorine will have 5. And neon has 6. Now, neon's full, so if we move to the next element on the periodic table, we're going to have to go and get, after the 2 p's is the 3s. So 3s would come next if we needed more electrons to put on. It's a pretty interesting fact. I'm always amazed how cool the periodic table is and how much information you can get from that. I'm going to get my arrow back. It turns out that we're giving you the order that the electrons fill. Upper level chemistry classes, however, aren't given that in on their information sheet. So they have to come up with some way of figuring it out. And it would be a pain to memorize. So one of the tricks we teach students is to look at the periodic table and just move from left to right. So the first area you're going to put electrons is in the 1s. And then after the 1s comes the 2s, and then after the 2s is the 2p, then the 3s, 3p. And here's where you can start to see the overlap, that the 4s's come before the 3ds, which then come before the 4p's. So upper level chemistry students kind of memorize this trick using the periodic table, but you're not going to have to do that. I just wanted you to see it, just to realize how cool the periodic table is. Valence electrons. I really should have this underlined for you because it is a vocabulary word that I'd like you to memorize. Valence electrons are those in the outermost energy level. They, the highest main energy level in the atom. So if you go back to visualizing the Bohr's model, where you have the nucleus and then you have all the orbits, all those energy levels around it, the valence electrons are the electrons in the outermost energy level. So it's kind of ignoring any electrons that are lower. For the representative elements, those are the elements that have A after their number in the group number. For representative elements, the number of valence electrons equals the group number. So all the elements, all of your alkaline earth metals that are in group 2A, all of them will have 2 valence electrons. So it's kind of a quick way of figuring out how many valence electrons. So here's a learning check. I want you to use the periodic table to determine the number of valence electrons in arsenic. And I do not have one to put up for you. So arsenic is in group 5A. Oh, I gotta get my pen. Okay, it is in group 5A. So you go to your periodic table, you find arsenic, you go to the top of the column and you see 5A. So that means there are 5 valence electrons. To verify the correct number of valence electrons, write out the ground state electron configuration for arsenic. Okay, so the first thing you do is you figure out how many total electrons does arsenic have. I don't have that memorized, so I'm going to look at my periodic table. And arsenic has, oops, I went too high, 33 total electrons. So we're going to do the electron configuration for arsenic. So we're going to take out your information sheet. You're going to look at the relative energies of your sublevels, and we're going to work that from left to right. So the first one you come by is the 1s. You have memorized s's can only hold 2. And we're going to just keep going until we've used up all 33 electrons. The next one is the 2s's. That can hold 2. Then comes the 2p's, and you have memorized p's can hold 6. Now we've used up 10 electrons, so we still have 23 to put on, so we're going to keep going. After the 2p's is the 3s, which can hold 2. After the 3s's is the 3p's, and those can hold 6. Now comes the 4s. S's can only hold 2. And then we have the 3p's. So that's where most people mess up, because they want to put the 3p's before the 4s. P's can hold 6. I'm going to stop and re-add up my electrons for a second so I don't go too far. Here's 10. 2, 6, and 2 is another 10. And then I have this 6. So I have to keep going. I have not gotten to 33. After the 3p's, actually that was a typo here. I meant to say 3d. Okay, that makes more sense. I wonder if I have an eraser. I'm going to peek real quick. Oh, there is. Okay, let's change this. I want to stop when we count. Okay. Okay, so let's say, back up in time, we've gotten to the 4s2s, we stop and we say, okay, if I count up all my superscripts here, I'm up to 20 electrons. So I still have to keep going. I'm going to look on my information sheet and see that it is a 3D that comes next. And you are going to have memorized that your D's can hold 10. So right now we are up to 30 electrons, so we have to keep going. After the 3Ds comes the 4Ps, and P's can hold 6, but we only have 3 more electrons to put on. Okay, so we have used up all 33 electrons. Now the question is, how many valence electrons does arsenic have? Now remember, valence is your outermost shell. Now in this electron configuration, the shell number is the number in front of the S, P, D, or F letter. So these are the shells. If I asked you what is the largest shell we're dealing with, I hope you would say 4. So how many electrons do I have in that 4th energy level? Well, if we add this up, I've got 2 in the 4s's and 3 in the 4p's, so that sums up to 5 valence electrons. So you can figure out that arsenic has 5 valence electrons by doing the electron configuration and looking for your outermost energy level, but the faster way is just going to be to go to your periodic table and look at the group number, and that'll tell you valence electrons. Okay, there is something called the electron dot symbol of elements that I want you to be able to draw. And the electron dot symbol shows the valence electrons around the symbol of the element. So an example here. So for magnesium, it has 2 valence electrons. So keep that in mind. When I ask you for the electron dot symbol, you're only giving me valence electrons. It's a common mistake for students to want to figure out the total number of electrons and put all those dots around. So you're only going to put on valence electrons, and you're going to put on the electrons using dots. So here is a couple examples. And all of these are fine for magnesium. Magnesium is in the 2A family. So I'm going to jot that down. So magnesium is in the 2A family, so that means we have to put 2 dots on. And there is certain rules to putting them on. Let me go over those rules real quick, so I don't want you to make a mistake. There's 4 regions where you're allowed to put your dots. You can either put the dots on the top, the right, the bottom, or the left. And that would be the first rule. Keep the dots in those regions. And the other rule is you don't pair them up until you have to. So it would be wrong to do magnesium like this. or like this, because you have 4 regions to put those two dots, and you don't want to put 2 of them in the same region unless you have to. Let me see real quick if I've got, oh, here's the example that was coming up next. Draw the electron dot symbol for arsenic. Okay, well, arsenic, we determined from the previous example, has 5 valence electrons. So we're going to put those 5 dots on. So the first thing I like to do it clockwise. I just kind of start on the top, and I put one on the right, then the bottom, then the left, and if I have more than 4, then I have to start pairing them up. Well, arsenic has 5, so I'm going to put that back here on the top. So I just kind of keep working around until you won't ever have more than 8. So this is the answer. This is the electron dot symbol for arsenic, showing the 5 valence electrons. It would have been just equally okay if you had your pair of electrons over here. What I'd be looking for if I'm grading it is that there's one pair and then 3 that don't have a pair. Okay, some periodic properties of elements. So properties of elements that repeat in a regular fashion as the atomic number increases. So one of these properties is the atomic size. It turns out that as you move from left to right on the periodic table, the size of your atoms gets smaller as you move from left to right in a period. And as you move from top to bottom, they get bigger. Okay, so the atomic size is described using the atomic radius. So that shouldn't be too big of a jump for you. If I've got a circle here, and I'm gonna depict 2 different atoms, and this has a bigger size than this one. So I could ask you which one has a bigger size, or I could say which one has a bigger radius. So it's kind of asking the same thing, because if I focus on the radius of this small one, the radius is from the center to the outside. And can you see that if you have a bigger radius, you're going to have a bigger atom? So I know that I can switch those words around and ask you which atom has a bigger radius or which one has the bigger size. It means the same thing. So, but you want to memorize the trend. You want to memorize that as you move from left to right, the radius decreases, and from top to bottom, the radius increases. Okay, I'm actually going to see if I can grab something else. It's totally fine if you memorize this trend. I'm going to show you how my brain prefers to have it memorized. I tend to like to keep my kind of the thing I'm focusing on the same. So I say if I'm focusing on the size, because that's what we're working on here, that my sides get smaller as I go up and my sides get smaller as I go right. So that's how I have it memorized. So smaller from left to right and smaller from bottom to top is the size. Size gets smaller. But it doesn't matter how you do it. If you like to do it the way your book is doing it, that's totally fine. So why is it that the size is changing? So the atomic radius increases as you're going down a group of the representative elements. So you're going to get bigger as you go down, like I said. And the reason that is because remember, you are putting on another energy level for every new row that you're in. So if you're in period 4, you're going to have 4 energy levels. Period 5 is going to have 5 energy levels. So it kind of makes sense that as you move down a family, the atoms are going to get bigger. Why they get smaller as you move from left to right is a little bit more complicated. It's an increase in the number of protons that increases the attraction of the valence electrons. So as you move to the right along a period on the periodic table, you're getting more and more protons. You're also getting an additional electron each move, so it might seem counterintuitive that the atoms are actually getting smaller. But what's happening is that there's something called the effective nuclear charge, and it's as if the charge is getting stronger as you move from left to right, so it's pulling the electrons in tighter. I'm not ever going to ask you anything about this. It's actually quite a bit deeper than the oversimplification I'm giving you. So basically you just need to know that as you move from left to right, the size of the atom is going to get smaller, and it's basically because the charge is getting more positive and pulling the electrons in. That's what's causing the atomic radius to decrease. So just know the trend. Okay, smaller from left to right, smaller from bottom to top. There is another property that has a periodic trend to it along the periodic table, and that is what we call the ionization energy. So the definition of the ionization energy is it's the energy required to remove an electron from the atom to form an ion. And in this case, it would be forming a cation, because if we're removing an electron, it's going to end up, the atom's going to end up being more positively charged. So and they have the first out here. The first ionization energy is how much energy it takes to remove the first electron. If you see the second ionization energy, that would be how much energy it takes to remove the second. But we're going to stick with just the first ionization energy in this course. If we look at some trends on the periodic table, so let's just look at our first period. In our first period, we only have two elements, hydrogen and helium. And what would we say about the ionization energy as you move from left to right? So let's look at our labels on our axes. Along our x-axis, we've got the group number increasing, and along the y-axis, we have ionization energy in kilojoules per mole. So remember, joules is a unit for energy, so that should make sense that we would have joules as a unit for ionization energy. So this is the ionization energy is increasing. So if we look at our hydrogen helium, we could say as we move from left to right on the periodic table, the ionization energy is going to increase. There are a few anomalies to that. Upper level chemistry classes need to be able to explain to me why boron is lower than beryllium. But for this class, we're just going to go with the general trend that as you move from left to right, ionization energy increases. That was not a very good straight line. So here's kind of a learning check for you. Where are the smallest atoms located? So on a blank periodic table, if I asked you to just kind of point to the region where you would find the smallest atoms, I hope you would say up here. Because the atoms get smaller as you go from left to right, and they get smaller as you go from bottom to top. Where are the largest atoms? Well, if the smallest ones are up here, the biggest ones are going to be lower left corner. Which atoms have the smallest ionization energy? Well, we said from the previous slide that ionization energy increases as you move to the right, and I'm actually just remembering that I forgot to tell you while we were on the slide that it also increased as you moved up the periodic table. So if you noticed, hydrogen was higher than lithium, which was higher than sodium. So you can look back at the previous slide. So ionization energy does the exact same trend where left to right and bottom to top, but with that case it increases. Where size decreases from left to right, bottom to top, ionization energy increases. So which atoms will have the smallest ionization energy? That would be down here. Largest ionization energy would be up here. Okay, so if I was going to like make a note card or something like that, for me, I tend to like this trend better. So I would say, using this trend, size decreases. It's going to be easier with my pen instead of the mouse. Size decreases, but ionization energy increases. Okay,